This lesson is on what's called differential equations. We all know what an equation is, but what makes an equation differential? Well, if it has a differential symbol in it. For example, this equation has a dy, that's a differential symbol. It has a dx, also a differential symbol. Now, while we traditionally have thought of dy dx as just a single symbol that involves the derivative, we're now, in the differential equation sense, going to treat dy dx as if it is a fraction. Now, there's some debate either way about whether dy dx is just the derivative symbol of a function or whether it is a quantity dy divided by another quantity dx. And it's a very complicated question that can't really be answered in this venue, but for the purposes of solving the differential equation, we're going to treat something that we've never treated as a fraction, dy dx, as if it were a fraction, dy divided by dx. We're going to use a technique here called separation of variables. That's where you get all your x's on one side of the equation and all your y's separated on the other side of the equation. So in order to do that, I did some work on scratch paper and I ended up with this. How did I get there? I multiplied both sides by dx, and I divided both sides of the equation by y. And what you'll notice here is that I now have what's called a separated equation. Separated meaning all the y's are on one side and all the x's are on the other. The benefit of separating your y's from your x's is that you can then apply the integral, or the antiderivative, to both sides of the equation, and this is going to ultimately lead us to a solution. So you'll recall, looking at the left side of the equation here, that the integral of 1 over a variable is the natural log of that variable. And on the right side, it's pretty easy to see that the integral of 6x squared is 2x cubed, and you'll notice that I put a plus c on both sides, but I didn't put literally plus c. I put plus a for one constant and plus b for the other. You'll recall that when we take an antiderivative, we always get plus a constant. And while we normally write that as a c, it would be a little misleading to put plus c on both sides here, because who's to say if those constants are actually the same? The constant on the left side could be vastly different from the constant on the right, and likely is. So what do we do with this a and b? Ultimately, of course, our goal is to solve for y, but we can simplify the a and the b by just putting a plus c on one side of the equation. So what we're really doing here is subtracting a from both sides, getting a constant b minus a on the right, and just calling that constant b minus a new name, call it c. And so if you ever see a professor, me or any other professor, writing plus c on one side and not the other when they do integrals, it isn't that they're forgetting to put plus c on both sides, they're just recognizing that adding a constant to both of them could then be consolidated into a single constant, which usually goes on the right, not that it couldn't go on the left. Now, you'll recall the absolute value of that's usually placed in the argument of the natural logarithm here. It's just the rule of the integral of 1 over y. In this case, looking at the top of the screen, they told us that y is the quantity greater than 0, that y is always positive, and therefore the absolute value of y would just be y itself. You'll also notice here that I did a trick from pre-calculus, getting rid of the natural log on one side by using the exponential function for the other. So, a couple of things going on there. Now, it wouldn't be technically wrong to stop here, but they've also given us what's called an initial condition. They've given us the fact that, look at the top of your screen here, that when x is 0, y is 7. So eventually I want to plug that in, but I want to show you a tradition first before I do that. You'll notice the plus c in the exponent here. There's nothing wrong with having a plus c there. But there's kind of a tradition that we get rid of that c and turn it into another constant. Watch this cool trick. You'll recall a rule for exponents, that when we multiply, we add exponents. So reversing that rule gives me this. But remember, c is just some constant. E is 2.71 something, as you'll recall. 2.71 raised to some constant power is itself just some constant. I'll give that constant another name. I could call it d to go alphabetically, but the tradition here is to call it k for no particular reason. And so I've rewritten e to the constant as some other constant, and I now have a more traditional solution to this differential equation. But again, look at the top of the screen in the original problem, and you'll notice that we have a specific condition, and that's going to enable us to solve for a specific y. Without that y of 0 equals 7 comment, if that weren't there, then we would be done with this problem, and we effectively would have found infinitely many solutions. Y equals any constant times e to the 2x cubed. But because we know that we want a specific function where an input of 0 leads to an output of 7, we can actually find a specific value of k. And let's go ahead and do that now by plugging in 0 for x and 7 for y. Plugging in that so-called initial condition, or that known information about the specific function we're looking for, enables us to now solve for k. After all, e to the 0 power is 1, and therefore this whole thing tells me that k is 7, and I now have a specific solution that matches y of 0 equals 7, and I therefore solved this separable differential equation.